Hello everyone, in this video I'll be reviewing question 2 on the 2016 AP Chemistry exam. So the first question states, a student designs an experiment to study the reaction between NaHCO3 and Hc2H3O2. The reaction is represented by the equation above. The student places 2.24 grams of NaHCO3 in a flask and adds 60 milliliters of 0.875 Hc2H3O2. The student observes the formation of bubbles and the flask gets cooler as the reaction proceeds. So first I want to write down the equation because it's given. And we're told that there is 2.24 grams of NaHCO3 and 60.0 milliliters of 0.875 molarity of Hc2H3O2. And there are bubbles. And the flask gets cooler. Alright, so part A. So this is number 2. 2016. Identify the reaction represented above as an acid-base reaction, precipitation reaction, or redox reaction. Justify your answer. So it's not a precipitation reaction because we know that a precipitation reaction produces a precipitate, and if we look at the states of matter, we only have aqueous, liquid, and gas. Since there is no precipitate, it's not precipitation. So if we look at one of the reactants, this is an acid. Specifically, it's acetic acid. Because we know that this is an acid, this should give us a hint that this is an acid-base reaction. But why is it an acid-base reaction? If we look at NaHCO3, when this dissolves, it will make Na plus and HCO3 minus. This ion is amphoteric. An amphoteric substance is one that can act as a base and an acid. If it was acting as a base, it would receive a proton to become H2CO3. If it was acting as an acid, it would donate its H and become CO3 2-. But because it's reacting with an acid, it will act as a base. So our response should be the reaction above is an acid-base reaction. Hc2H3O2 is a weak acid and it reacts with HCO3 minus, a weak base. So this question tests your knowledge of the types of chemical reactions and how to identify them. You get 1 point for mentioning that it's an acid-base reaction and 1 point for your justification. Part B. Based on the information above, identify the limiting reactant. Justify your answer with calculations. So we're given the grams of NaHCO3. So we can use conversions to find how many moles of it there are. So when you use your reference table and your calculator, you'll find that the molar mass of NaHCO3 is 84.08 grams. We want moles, so we put that at the top. Grams cancel with grams. Put that into the calculator. We get 0.0267 moles. We rounded to 3 significant figures because in our question, the lowest number of significant figures is 3. Next, we want to convert this into moles. So we have 60 milliliters. Liters at the top, milliliters at the bottom, because you want milliliters to cancel out. And then we have molarity, which we know is moles over liters. So 0.875 moles of acetic acid over 1 liter. Liters cancel liters. We'll put that into the calculator. We get 0.0525 moles. And this is perfect. Because we want exactly 3 significant figures. So when we compare the moles, there's less of NaHCO3, so that's our limiting reactant. So we have to answer the question. The limiting reactant is NaHCO3. So this question is testing our knowledge of stoichiometry. And you get 1 point for showing the math, which counts as your calculation, and for answering the question, because it does say identify the limiting reactant. So there's 2 points here. Part C. The student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of the collisions between reactant particles. Alright, so we know that at the beginning of every reaction there is more reactants than there are at the end. So they ask us to explain this in terms of collision, in terms of the collision theory. So what I would say is that as the reaction continues, more reactants are being used to make products. Since fewer reactants remain, collisions become less likely, and thus the bubbling gradually slows. So as long as you mention that reactants are being reduced, and so because there are few reactants, there's less reactions happening, and so there's less collisions, and therefore the bubbling stops, you get 1 point. Part D. In thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Part 1. Considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction between NaHCO3 solid and HC2H3O2 aqueous? Answer by drawing a circle around one of the choices below. So, a key thing they said is thermodynamic terms. And we're given three choices: enthalpy, entropy, or both of them. So, and they also say that the flask gets cooler. So when I first read this question and I read flask gets cooler, I thought, oh, enthalpy, right? Because there's a change in temperature. But it's very important to note thermodynamic. And when we hear thermodynamic, we should think of this equation. Delta G is equal to delta H minus T delta S. So we know the reaction is happening in a flask, right? And a flask is a closed system. In a closed system, there's the system and the surroundings. In this case, the system would be the reaction and the surroundings would be the flask. So if the flask is getting cooler, that means the heat is going into the reaction. And if it's going into the reaction, that means the reaction is endothermic. And the sign of H that correlates with endothermic is positive because we're bringing in energy. So, a thermodynamically favored reaction has a negative delta S, right? So if we want, a negative delta G. If we want delta G to be negative, right? We need this side to be negative as well. So if H is positive, that's not going to help us, right? And we haven't really talked about temperature. But if delta S is positive, right, and then it multiplies to temperature, it will be a large negative number. And if we add it to this positive number, the whole answer would still be negative. And that is why entropy is what drives this reaction, because for delta G to be negative, delta S has to be positive. So it depends on the sign of S. Part C tests your knowledge of kinetics, and you get 1 point for your explanation. Part D tests our knowledge of thermodynamics, and you get 1 point for choosing entropy. So there's a second part to part D, and they want us to justify our answer to this question. So I'm just going to restate. You would just restate your thought process of why you chose entropy. So we can start by saying delta G is negative when a reaction is thermodynamically favored. Since the flask gets cooler, we conclude that the reaction is endothermic. According to the equation, delta G is equal to delta H minus T delta S. If delta H is positive, delta G will only be negative if delta S is positive. Therefore, entropy is what drives the reaction. And you receive 1 point for your answer here. Part E. The HCO3 minus ion has 3 carbon to oxygen bonds. Let's note that 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third carbon to oxygen bond is longer than the other 2. So of these 3, 2 have equal length and 1 is longer. The hydrogen atom is bonded to one of the oxygen atoms. So there's an H2O bond. In the box below, draw a Lewis electron dot diagram or diagrams for the HCO3 minus ion that is consistent with the given information. So we know there are 3 carbon to oxygen bonds, so we can start with that. C for carbon, and then it's attached to 3 oxygen bonds. Right? Okay. And then there's an H bond. Actually, I think the first thing we should have done here is to find out how many electrons should be present in total. So we know H has 1 valence electron, C has 4 valence electrons, O has 6 valence electrons, but there's 3 O's, so that's 18 electrons. And since the whole ion is an anion, we know it gains an electron, so we have to include that as well. When we add this up, we get 24 electrons in total. So far, we have 1, 2, 3, 4 bonds, which total up to 8 electrons. So we want each of our atoms to be satisfied, right? They have to obey the octet rule, which means they have to be surrounded by 8 electrons. So H is good because it only needs 2 valence electrons to be satisfied, but the 3 O's and the C are not. So since we have 8 electrons so far, let's count up to 24 and see what else we can do after that. So we have 8, 10, 12, 14, 15, 16, 18, 20, 22, 24. So we're out of electrons. But we notice that this O, that O, and C are all satisfied, but this O is not. So we have to help it become satisfied. Since C and O make a covalent bond, they can share more electrons, right? So we can create a double bond, which would make them share 2 pairs of electrons in total. So now, let's see how many electrons we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So there's 1 more pair left. So we can use that here so that this O is happy too. So when we look at every atom now, it's happy. And that completes our structure. But do not forget the negative sign, because this is the Lewis dot electron diagram for a polyatomic anion. So we're not done yet. In the question, they kind of give us a hint, right? Diagram or diagrams. So when we look at the diagram we have now, we could have put this double bond here, right? And the ability to move this bond around is called resonance. So we can draw one more diagram. And the only difference would be that the double bond would be here. And that would be our resonance structure. So H to O to C to O to O. To O. And then we have our electrons. Everyone's happy, and the negative symbol because it's an anion. And please, please, please do not forget to make one of the bonds longer. So I just made this ones longer, and then these two equal, because that was one of our requirements. So this question tests your knowledge of drawing electron dot structures, and you get 1 point for the correct diagram, and you also get 1 point for showing the resonance structure. Part F. A student prepares a solution containing equimolar amounts of HC2, H3O2 and NaC2H3O2. The pH of the solution is measured to be 4.7. The student adds 2 drops of 3 molarity of HNO3 aqueous. So I'll take some notes first. We have equimolar, meaning equal molar amounts of HC2H3O2 and NaC2H3OH. The pH, the initial pH is 4.7, and the student adds 3 molarity of HNO3, nitric acid. and stirs the sample, observing that the pH remains at 4.7. Okay, so and pH is the same. Write a balanced net ionic equation for the reaction between HNO3 aqueous and the chemical species in the sample that is responsible for the pH remaining at 4.7. So that last phrase, pH remaining at 4.7, hints at this being a buffer solution, right? So this question is testing our knowledge of buffers. And we know that the function of buffers is to control pH. So why is the reaction between NaC2H3O2 and HC2H3O2, why does it make a buffer? So we know that buffers either happen between weak acid with the salt of its conjugate base, or a weak base with the salt of its conjugate acid. So the question wants us to write a balanced net ionic equation for the reaction between HNO3 aqueous and the chemical species in the sample that is responsible for making the pH stay the same. So we know that they're adding nitric acid, which is a strong acid, very strong acid. So first we'll have that. What's that? Because they're all together now. And I'll just make the arrow going down because I don't have space to the right. And it goes both ways because there is a weak acid involved. Since we know that the weak acid does not completely dissociate, it will stay the same. So if we want our net ionic equation, and we know that this one completely dissociates, we know that the H will be donated. And this is aqueous, and it's an ionic compound, right? So Na will dissociate, and this will be left alone. So we combine those two. We combine the H and the base here. Because when this H when it dissociates from the compound, it wants to look for a base, something that will accept it. So this becomes our net ionic equation. Again, double arrows because we're making a weak acid and there was a weak acid involved at the beginning. So for this question, we receive 1 point for the correct equation.